Yeah, so I'll take you through a little bit about what Intel is doing in HPC and AI, because it's kind of related for us. We think that they will converge at one point of time. So before I start, I wanted to give this slide. Usually I love this slide. It explains why I have this passion for HPC. HPC touches the lives of every single person on earth. Touches my life, your life, everyone's lives. You know, the gas you put in your car has HPC element in it. The water that you drink, the medicine that we take, anything that you can think of, many things that you can think of is related to HPC, environmental protection, all of those. So this is just a subset of the things that we can do with HPC. And this is why I'm personally passionate about it. So if you can look at it, I'm particularly interested in, is there a light in this one? Yeah, there is. I'm particularly interested in improved cancer treatment because I lost many people dear to my heart due to cancer. So that's why I'm passionate about this technology. I've been in this field for more than 20 years and I really love it. So now what Intel is doing in HPC. So this slide summarizes almost all of our products in HPC. I'll go a little bit in this slide, and then I'll dig a little bit deeper in some of the technologies that exist here. And if you need any more in-depth discussion of any of the things that I'll talk about, you can either ask, or after the session, we can talk, we can have a side discussion, or we can have separate meeting as well, online meeting anytime in the near future. So let's start with this. Processing, it's the heart of Intel. Okay, Xeon is the heart of any data center that you can touch. It has more than 70% market share today. And it runs on almost any data center that you can see. You'll see Xeon in there. And it has some competition today, but we are doing really fine with Xeon. We'll talk about what's going on with Xeon now and next. After that, we announced our Intel Data Center GPU. It will be that we started shipping it already. It will be in the market for general availability next year. Watch out for that. I'll talk about it a little bit in my slides. And then Habana. Habana is a company that we acquired. All what they do, they manufacture AI-specific ASICs. So they have two ASICs, one specific for training and another for inference. So and you know, as per Amazon CEO, it gives 40% better price performance than the competition in AI, especially in training and inference, of course. Movidos is an edge device, vision processing device, and Stratix is our FPGA business line. Next, all of this needs to be programmed somehow. So we have the One API initiative. Okay, that is an open standard initiative. It's not an Intel initiative, it's an industry initiative. However, we have our own implementation of it, just like Red Hat and Linux. Linux is an open source, something that you see everywhere. And Red Hat is the variation, or SUSE or whatever, is the variation that they sell support for. And that's exactly the same model we are following with One API. I'll talk about it soon. The whole concept of One API is that you can program your CPU, GPU, FPGA using the same programming environment. And then in the storage side, Intel Optane, if you didn't hear about it, is basically a 3D cross-point storage technology that we came up with Micron jointly. What it does, as you can see, it looks like a DIMM, memory DIMM, that you can slot into your memory bus and will act as either really fast storage or a little bit slower memory. And then for the interconnect, CXL is probably the most interesting one here. It's called Compute Express Link. It enables memory coherency between the CPU and the accelerators. So basically, there will be accelerators very soon, or even with the storage very soon, that will be memory coherent between the CPU and the accelerator, whether it is GPU, FPGA, or whatever accelerator is in there. And the manufacturing innovation, EMIB and Fevros, I'll talk about those, but those are really state-of-the-art engineering in physics for processor design. What they do, EMIB is 2D connectivity for chiplets. I'll show you in a minute how it works. And Fevros is a 3D connectivity for chiplets. We'll see that in more details soon. And of course, security is everywhere. Any question on this slide? It's very important that we get it well. Go ahead.
So just one question with one API, which I know people in my group have explored, but you said I can use the same program of abstraction. So does that mean that you? So the question's really, when I start thinking about communication off of the processor, off the GPU, and I start thinking about the different levels of cache and memory coherency, how does that really keep track of it? Do you have like GPU aware so that if you're going from one GPU communicating to a different one, even a different node, it's going to do that outside of MPI? And then if I'm trying to do some communication with memory, like an RDMA, is that going, how does it handle that? Or do I also have to program that aspect with one API?
Oh, so basically one API, as you're probably aware, since you played with it, is based on SYCL. So offloading and unloading to the CPU is based on SYCL standards. Now, what you are asking for, is it how to offload? Then we have what we call Intel Analyzer that will tell you which part of your code that you can offload. I'll come to that in one of the slides.
I know what you're asking. You have to do it explicitly. I'm not even sure if it's implemented yet, to be honest with you. We've talked about GPU direct enablement on PVC, and you get woolly answers. We have to follow up with that, actually. It's work in progress, yeah. Yeah, there's stuff I can talk about offline, not inline, not in public, about other groups that I'm aware of that are looking at this. But it's a significant feature that you have to explicitly deal with.
Thanks, Paul.
Also, you've got, especially in your domain, GPU direct storage type functionality is another. If you want to do your I/O without going through the CPU level as well.
Yeah, it's really GPU aware.
Yeah.
But that's so much explicit.
Like with the MPI, the work that DK Pan has been doing for years, right? I've been discussing this with DK, by the way. So yeah, I guess it will have to be there.
Yeah, thank you. Okay, so let's look at the roadmap quickly. As I said, today we have the 3rd gen Xeon processor, codename Ice Lake. It's shipping, it's in the market. You can see it in top 500. Early next year, actually January 10th, we are launching the next generation, which is codenamed Sapphire Rapid, and it will be our 4th gen Xeon processor. We'll talk about it shortly. And Xeon HBM, which is Intel Xeon Max, we call it. We are coming to that. And then the Pontifex, which is our next, which is upcoming GPU. Now it is named Intel Data Center Max GPU. And then we have, of course, a roadmap to follow after that. So let's start with the Xeon. So the next gen Xeon, which is Sapphire Rapid, the 4th gen Xeon, the interesting part is probably it will have many accelerators. So it's the only CPU that exists today that have an AI accelerator built in. So basically, you can do your AI on Xeon. It will be good enough. and you can start with that. It is in your data center anyway. It will be this Xeon in your data center anyway, and then you can start doing your AI, whether it is training or inference, accelerated within the CPU, hardware accelerated. And we have some software optimized versions of Python, PyTorch, Python, TensorFlow that you can use and make use of those features. It has a really big last level cache, more than 100 megabyte. It will be DDR5 enabled, 8 memory channels, so you will get a boost in your memory bandwidth. That's the regular Xeon. Now, if you go for Xeon with HBM, you will get high bandwidth memory inside the CPU. I'll come to that in the next slide. Okay, the advantage of that is basically you'll get 4 times the memory bandwidth of a regular Xeon. It's really big for HPC, some HPC applications, especially those that are memory bandwidth optimized. So in the next slide, I'll talk about the technology here, and that is what I want to go. So EMIB, we spoke about it. Who remembers EMIB? I spoke about it the first slide. Okay, good. It's the 2D connectivity for chiplets. So if you can see, there are 4 chiplets connected via EMIB, and there is HBM high bandwidth memory within the chiplet. Okay, and that is how we design our Xeon with HBM. I really like it. It's a lot of engineering went into that. And next, go ahead.
So what's the trade-off in core count? The non-HBM, the fastest, in terms of clocks, versus what do I have to sacrifice for the power cost of HBM?
The delta is not in the number of cores. So number of cores will stay the same. Yes, we can take it offline and under NDA, but yes, there will be a difference.
There is a floating cost.
Yes, there will be.
And that cost is because of the
yeah, there will be a cost. We can take it under NDA after the session immediately. Yeah. Yes. Yeah. So
if you have memory bandwidth cost, that was a good trade.
Hungry apps, then you might be better off with the non-HBM.
I agree on that.
So you should have probably some heterogeneous Sapphire state where you put your non-memory bandwidth hungry on the normal. Yeah.
So it depends actually if you are. So I know some customers that have specific application, single application that has extremely memory bandwidth.
Yeah, of course.
Then those are for HP.
That's easy for them.
And there are others like research institutes and something like that that have both some memory bandwidth application and none. And this is where you need 2 partitions, as you just explained.
Yeah. Super. Thanks.
Yeah.
So one other question.
1 minute. There is a question
on the HBM connectivity to each chiplet, and what happens if what's the penalty going to be if you're loading more data than the HBM directly connected to the chiplet can hold? Is it going to span over to other HBM, and is there a mesh network allocation in there that takes care of that?
Very interesting question. So basically, HBM can act as in 2 modes, either as a cache to your DDR5 memory, and this is where it goes into your memory hierarchy, or in flat mode, where you have to explicitly program what part of the code, which part of the data goes into the HBM. There is something called fmalloc, fast memory allocation in C, where you can put it in HBM, specifically pin it to the HBM, or it will go to the regular memory.
So you would have to address that always on a chiplet boundary to fill the HBM directly connected to that chiplet.
If you get it in flat mode,
Yeah,
yes.
yeah.
If you get it in cache mode, you don't need to do
care.
anything.
Yeah, you don't care.
The operating system will worry about
Yeah,
it.
yeah.
Question in the back?
In the back.
Oh, yes.
So what I'm interested in is, I mean, everything.
Sorry?
Oh, okay. So what I'm interested in is essentially, you know, when I saw the conversions going over to accelerators, GPUs, a lot of the acceleration was because of HBM. And again, it's dealing with cache and what can remain in cache. If I do have some sort of kernel, which all the memory does fit in. So usually that would be more AI than some of the HPC focused, which would then be MPI communication. So if I have that, and now I just take something which remains fully within HBM and occasional coming in and out, if I compare that to now on some of your GPUs, what's, you know, what's the benefit of the GPUs compared to now CPUs given HBM?
So the thing that I might think of that will be the benefit of the GPU over CPU is the flops. So this will not have as much flop as the GPU. GPU will have HBM and a lot of flops. This one will have HBM, but much less flops. Okay, so the cost factor now for this is the advantage. This is much cheaper than a GPU.
Okay, we can take some of that offline.
Sure.
Scott, I've been doing exactly the same. There's a lot of advantages we get from GPUs because of the memory bandwidth. So in those things, I mean, the reasons like GPUs are perfect is because you have to move in and out. Yeah. So now if I can bring me fully in, but I can't take full advantage of the flops in the GPU for those pieces. It seems like it's going to even out.
I think this is going to, make that paradigm less valuable.
Yeah.
Yeah, I've always, for a long time anyway, if you have a cross section of codes, and this is work I'm doing again now, and you run your codes on an Ice Lake, and you run your codes on an NVIDIA A100, and you look at the performance delta, and you look at the price delta, it is tenuous at best. Yeah, I've been using this in conversations with my NVIDIA colleagues for years in terms of what should their price point be. It only works if you're doing AI. Simulations, it doesn't work. So you guys here are going to have to end up eating your own dog food. It's your ecosystem. You're going to see this already, I'm sure. Yeah. That the price performance advantage of a Ponte Vecchio is slim, but you can of course adjust the price point to make it better. NVIDIA won't do that. Yeah, so this is an interesting area, and the whole GPU paradigm is tenuous when you start doing this kind of analysis, apart from certain workloads where you get a 10x. Always in history, I have said, if the accelerator does not give you a 10x, it will not work economically. Yeah, look at all the accelerators that have come and gone and died because they didn't have that 10x over the commodity. If you haven't got the 10x, you're going to die. Yeah, AI has that 10x. Simulation workloads do not. Yeah, so this is I exactly agree with your point, Scott. Yeah,
Xeon Max.
You know, Xeon is one of those things that just.
How long do I have?
Xeon is
10
unstoppable.
minutes? Okay. So
we've used up a lot of your question time already, so you can extend a little bit.
Oh, it's okay.
You have my permission.
Thank you. I've got the permission of the boss. Thank you. So Ponte Vecchio, I'll not go into some benchmarks, but I want to show you what Ponte Vecchio is capable of, which is our upcoming GPU. Okay. What I like is that it has 128, where is it? Gigabyte. Is it there? No. It has 128 gigabyte of HBM. I don't think there is an accelerator today that has 128 gigabyte of HBM. The maximum I've seen probably is 80 gigabyte for HBM. So it's, if you have bigger workloads, then this one will be really good. It has 128 ray tracing points as well. What I like about it is the big cache, more than 400 megabyte of cache in Ponte Vecchio. Again, it's the biggest in the market today. XE-Link, I'll talk about it in a minute. Now, Fivros is the one that I promised you I'll talk about. We spoke about EMIB, which is a 2D connectivity of the tiles. Fivros is the 3D connectivity of the tile. If you can see, EMIB is connecting the chiplets between each other. Fivros is connecting them, is stacking them up. Okay, so that's an absolute innovation in technology. Okay, I really love that. So because of time, I'll go next. No, I have to show you this. I like this number. You know, if you look 5 years ago, okay, we didn't have fraction of this number in a chip. This one has more than 100 billion transistors. It's amazing physics in there. And XE-Link basically is the interconnect between the GPUs. You can connect up to 8 GPUs in a full interconnected mesh, or you can connect 64 GPUs, like one each. A0 silicon, which is a pre-production silicon that we already have in the labs, okay? Look at the numbers that we have, more than 45 teraflops. That is peak, we mean, okay? More than 5 terabytes per second for memory bandwidth, which is really big, I assume. Just to put this in perspective, okay, our HBM, oh, I cannot say that, it's in NDA, okay, but that is really big, okay? Today, Ice Lake is not NDA. Ice Lake is around 200 megabytes per second. And this will give more than 5 terabytes per second.
You say publicly that HBM uses HBM2E, and we know the theoretical max.
Yeah.
So,
Yeah, exactly.
so that's what you can refer to.
3.2 megabyte, a gigabyte per second. And that is more than 5 terabytes per second. And the connectivity bandwidth for the XE-Link is more than 2 terabytes per second. And Falcon Shore, okay. John Laurent in his keynote announced that sometime in 2025, we are coming up with our Falcon Shore, which will combine both GPUs and GPU cores and CPU cores in the same chip. So you'll have some CPU cores, some GPU cores in the same chip, with HBM, obviously, in the same chip. And all of those, we call it XPU. The promise of Falcon Shores is more than 5x the performance of today's technology. In 2025, that is in 2 years, because we are already 23, I guess. And yeah, you want to take a snapshot? That is what Raja said, so I'm following Raja. Yeah, and finally, how we program all of this. As I said, one API is an industry initiative. Intel has a variation of one API, implementation of one API that you can download and use for free. Okay, in case you need some support, we will sell you the support. But for now, you can go to intel.com. The link is here when we share the slides. You can just click on this link or just go intel.com/oneAPI and download everything and play with it. The promise of one API, or not the promise, what we do with one API already is that you can program your CPU, GPU, and FPGA. And by CPU, GPU, and FPGA, we don't talk about Intel products only. Non-Intel products will be programmed using one API. Will be able to program. You will be able to program using one API. Sorry? Few moments? Yeah, sure. Okay. Just highlighting the compatibility tool, and I'll be done. The compatibility tool in one API, what it does, it migrates your CUDA code. If you have a CUDA code to one API automatically, it does more than 90% of the migration automatically. And then like 5 to 10% you'll have to tweak manually. I will not go into this. Thank you very much. If you have any questions, I'm willing to hear. Otherwise, it's over to you.
Just a comment. So my group has been working extensively with one API, and we find it really, the RSCs find it really useful for developing code across targets. We have some academics using one API to port code to NVIDIA, and they're getting very similar performance to native CUDA code. So we find that one API is very well received within our research software development teams. As usual, they're used to the internet environment anyway, of course.
Yeah.
And we find it very valuable. So I think this is probably in the long term more powerful than a particular point solution of a GPU or an x86 device. If we get this right, it enables many things.
Yeah, the whole idea is to get you out of vendor lock-in.
Yeah.
You can use any vendor hardware using one API. Thanks for that comment, Paul. Any other comment, question? Quickly, we have 1 minute.
How will one API integrate with various professional software development like CI/CD packages or Jupyter notebooks or something?
I don't know about CIDC, but Jupyter notebooks. Jupyter notebooks is like a little bit higher level.
I mean, the code it generates, you could deploy via CIDC methodologies, of course, but I'm not sure whether that's. I can't figure out that kind of join. But obviously, the code you produce, you could run from within.
It's a legit question that's coming up for us in our research. We're trying to figure out software development across HPC, and I was surprised to find across the ISV community how many people are using general enterprise computing tools like CI/CD.
I used to be surprised when users asked me silly questions, but I think users just.
It's not a silly question. It's what I'm telling you. It surprised me to find out how many people are doing this.
Doing what?
Doing general enterprise software development tools that you don't typically associate with
one API. I would want to integrate with Jupyter Notebook. I can't figure it out.
Okay.
To do what? Using Jupyter Notebook to do what?
So instead of OpenMP, so think of instead of using, like we use sometimes OpenMP in our Jupyter notebooks, we use MPI. Now imagine that you have a higher level abstraction that if this could work, then you can just use this abstraction and then you can get more acceleration. I think that's where people are looking at.
And maybe I'm just too old and stupid. I don't know.
Let's take that offline.
Let's take that offline.
Yeah.
Okay.
There's a question. I don't know.
NumPy. If I understand correctly, NumPy and one API work together, and a lot of the Jupyter Notebook.
NumPy is part of Python optimized libraries for one API. You are right.
That's correct.
Okay, we'll talk about it offline. Thank you, Paul.
Thank you very much.
Thanks, everyone.